Hi everyone, hope you're doing great. My name is Gabriele. Here I am. I come from Italy, which you can tell by my name, my accent, or the fact that I usually wave my hands around a lot. Well, bear with me, don't get distracted. So, a few things that I do, double-clicking the thing by mistake, that's one thing. Other things that I do by day, I'm a software engineer at Buildo, which is a consulting company. We do complex web applications using Scala and JavaScript. In Milan, a few other things, this once by night. I organized the Milano Scala group, which is the user group about Scala in Milan, and the Scala Italy Conference, which is this year in May in Rome. So if you want to come to a conference in Italy, maybe this is your conference. So, about this talk. Why am I doing this talk and what is this talk about? So this talk is about monad transformers. That was in the title. What is talk I wish I've seen, and there's a few others, mine is not the only one, about monad transformers in general. Because they're a complicated topic to face without a preparation of any kind, and it sucked the first time I actually had to face them. Why am I doing this talk? I'm not a functional programming super guru. I'm just learning like anybody else. And I still remember how it was, how much it sucked to get into the topic without a preparation of any kind. So I hope this talk gives you some basis to face this weird concept of monad transformers with some kind of knowledge that helps you getting your day a little bit better when it happens, if it happens. So, everything starts from a question. The idea of this talk, in general, the concepts that I'm going to explain from now on. And it's not a very complicated question. It's a Stack Overflow question. I'm going to boil it down for you. So the problem this question had was a silly problem. Was like, but it had some core hidden within it. So it was, okay, I have this future of a list of int. And I'm doing this map because it's a future, right? I need to get into the future, and when it's ready, I'm going to do something with the result. The result is a list. I'm going to map over the list. And the guy was like, that's weird. I'm doing two maps. So the only reasonable answer to this problem framed this way, well, the question was actually, can we do any better? But the only reasonable answer is, well, just indent it. I think that was a very reasonable answer, and it was already there when I got to the question. And I thought it was great. I upvoted it, and then I thought, well, I'm going to get my piece of cake too. I'm going to get some points because it's Stack Overflow, and I love getting points on Stack Overflows. So let's apply some science because it works. And I'm not going to swear. But let's consider for a second that map on future in Scala is a method on a future, which is a class. Nothing fancy about it. But you can actually interpret it in a different way, and some libraries we will see do. And as you can think of future having an instance of a functor. And a functor is a data type that essentially has some laws to respect, but the main thing is that it defines a way of mapping over something. This is a very stupid and silly way of describing it, and there's more complicated and rigorous ways to do, and I'm not going to do any of those today. So, if you have a functor for a future, you know how to map over futures. If you have a functor of a list, you know to map over lists. This is not true in Scala. You can map over lists without the concept of a functor, because it's implemented that way. But for a second, pretend that you have two functors. Functors, from category theory, compose. So what does it mean? It means that you have a functor of a future and a functor of a list. If you have a future of a list, which is the composition of future and list, actually of list and future, if you compose the two functors, you're going to get the functor of the composition, which means this, essentially. You can do this and this. You want to know how to map over a future of a list in just a single shot? Just take the two maps that you know how to do, the future of and a list, and compose them together. That works for functors. That's easy. And it's a single map, and you can actually do it with a library, which is cat in Scala. And this is actually code that compiles. You can copy paste into your REPL. And the main line, apart from the imports that I made just to make this code importable, copy pastable, leads this one here. Future of list of f is what I said it was going to be. It's a functor of a future, compose the functor of a list, and it gives you the functor that can map over this thing here, which is a future of a list of int. And just one map. A lot of points on Stack Overflows, for real. Without any sense, because this is clearly the wrong solution to that specific problem. But before going any further, I mentioned cats. Cats is a library from type level that brings some category theory concepts to the language. It interprets the data structure that the language has and some others within the context of category theory. It's not the only one. Scalar Z is the other famous one. It's much older and it's been around for much longer. The two libraries are essentially equivalent in the scope of the talk I'm giving today. So I'm not going to delve into politics of which one you should use, but you know that I'm using cats in this talk, but you could use Scalar Z, same thing. Essentially, it's also same syntax apart from some minor differences. So let's talk about flattening things. So if you have a list and you're mapping and you're adding one to a list of integers, you get, well, the same list, all the integers are going to be bumped by one. Awesome. Amazing function programming. Then, if you have a map operation that returns another list, though, what you have is the list of lists, which may make sense for a list. But sometimes you want to flatten it, so you want the flattened list. So you do map, you return a list, and then you do flatten. And flatten works because if you have a list of a list, it just combines them. It knows how to combine lists. Well, map and flatten is actually a pretty common pattern that has been encoded with a fantasy name, which is FlatMap. And flatten plus map is FlatMap. Flatten compose map is FlatMap. So instead of doing map and then doing flatten, you can directly do FlatMap and directly return a list, and this is going to be the same thing. So what is the lesson here? A very important one. So if you find yourself having an f of something, you probably want it to FlatMap. That's a very stupid lesson, but it's not so stupid. So when you find yourself trying to chain stuff like futures, you may do map. And that's a stupid idea because you're going to get a future of a future, which doesn't mean much. It may mean something in some contexts, but it's usually not what you wanted. You want it to FlatMap. So FlatMap kind of allows you to chain stuff without nesting the final result. You're nesting stuff, but the final result is going to be flattened, which is a good thing, which is usually what you want. If you have an option of an option of an option of an option of an int, it's probably not what you wanted. So FlatMap, I introduced it as a convenient, silly function that does two things together. It's actually a much more powerful concept, which is at the core of the definition of what a monad is. Again, I'm not going to go into the details of and the specific definition of what a monad is, but you can think as map stands to functors as a core operation, FlatMap and belongs to some other operation and more complicated laws is what defines what a monad is. So let's take a slightly less contrived example. So suppose you have to get a user, let's say from a database or from something that returns the user in a future, because it's an asynchronous computation. And then you do the same thing with the address, maybe because it's another cluster, another database, so it's asynchronous. So you want to get a user, pass the user to the function that gets the address, and then get the address back. And maybe to extract the city at the very end of it, which is a field of the address. So what you can do is actually a very sensible thing. We've seen that we want a single future as a result. So we FlatMap over the first future, then you get a user, then you pass it to the address, then you map over it, and then you get the city. That makes sense. And that is so common in Scala and other languages that the language has a special syntax for it, which is the for comprehension. You may have seen this. Maybe some of you didn't know that behind it is just a bunch of flat maps. There's actually a step of the compiler that translates this code into this code, more or less. And you can do this. You get the user, there it is. You get the address, there it is, and then you extract the city. Same code, exactly same code, just written in a different way. So the lesson here, before we go further, is that monads allow you to do sequential execution, to chain stuff together. And they have this characteristic intrinsically that they can squash something that has an f of an a into an f of a, which is actually the join operation, which is another way in which you can define a monad. So we're done, right? Any questions? Everything's nice. You can squash things together. You can chain things together. But if you hold on for a second, what about these kind of things, which are the nasty ones? If you have an f of a g of x, let's say this, Let's take this example. It's the same one as before. Are you really gonna get a user when you look for it? Not always, right? Sometimes you don't get it. And you want to represent that as an option, because the future represents the computation may fail for some reason, maybe the network, maybe some kind of other accident happened, but then you want an extra level of semantic, which is, I successfully looked for the user and it wasn't there, trust me. So this is actually what you would have done in your code base more reasonably, so this is more real-world example. So now you do the same thing and it fails miserably because the getAddress method functions what wants a user. And Gab here is not a user anymore. It's an option of a user. You cannot just pass it down like this, right? Damn, I need to ship this code tomorrow, so it's gonna be like this. And we're done, right? Success, yay. Or, well, with function programmers, we really like the for yield syntax, so we're going to do this and go home. Never do this. I'm not even sure it compiles, but it should. You can actually do this. It's a silly way of doing that. So, we've learned something before, that you could actually take a map of something, the map of something others, combine the two capabilities, and get superpowers by combining them, and get a super map function that can map over a composition of the things. Essentially, we're doing the same thing here. What we want is a flat map that can map over future of options of something. Not just future, not just options, we can merge them together, right? Something like this. This is the same example as before. I can flat map over a future, I can flat map over an option, just mix them together, and we're done. No, sorry. You cannot do that, at least not generically, not by the virtue that two things are the same, are just a monad. Knowing that two things is a functor is enough to compose them together and get a functor of the composition, which is the data type you're interested to map on. And monads do not have this property because they are a much more powerful concept, and with power comes limitations, not responsibilities, but also responsibilities. But essentially, they do not compose. This is a link to a blog post that explains that in very few complicated lines of Scala. So, sorry, we're done. And what is actually, if I'm going to click this, it's going to do it twice, right? OK. So what is the impossible part here? Essentially this. What I said before, two things are two functors, no problem. I'm going to get you the functor of f of g. I don't need to know what f is, and I don't need to know what g is. I just need to know they have a functor in scope somewhere. You cannot do the same thing for monad. That's it. It's a very core difference between expressive powers of these two things, which brings some limitations in. So generically, you cannot compose, which is essentially, generically, it's a weird term, I realize, because composing means generically, otherwise you're not really composing stuff. But you can compose them specifically in the sense that you can obtain the composition of the two things and work on it. You can actually do it. So let's take a feature of an option and wrap it around a wrapper class. Well, I use a FutureOpt class to wrap around it. If we can define a flat map and a map operation for this data type here, you can essentially piggyback your future of option and place it into FutureOpt, which has a map and a flat map, and you can just use it in a for comprehension and then take it out. So let's try to do that, and it's fairly easy. This is in cats. I'm not going to go through this, but I was able to do it, so it's easy. Okay. And you can use it like this. It's a case class, so you get for free the apply method, so you can just wrap your method around this FutureOpt, and it works. Trust me, it works. Essentially, what you get is a future of opt string, and then you just get the value out of it, and it's that value. So what you've done is to wrap things inside a special constructor, in this case, work within the context, which is easier to work with because you have a flat map that is defined for the composition of the two, and then get the value back at the very beginning, at the very end. So what if you need to do something slightly different? You don't have a future of an option, you have a list of an option. Well, OK, let's do the same thing, list opt, same trick, same thing. Does it look familiar? Right? It's the same thing. I'm just literally changing list with future. And this is actually, we accidentally invented the monad transformer by doing this. So why OptionT is the first one that we're going to see, first one of two, spoilers. And OptionT is essentially using the same concepts that we see now, but it's more powerful in the sense that we realize by doing our examples that you don't need to know anything about the monad that is outside, let's say, the monad that it comes after the one you're caring about, which is option in this case. If you see the examples before, we're not using any special information about future here, for instance. We just call him pure and we call him map. Nothing that tells us anything about future specifically. We only have some specific knowledge about option. We know how to deconstruct an option, and this is going to be different if option changes. This is the core of why you cannot just compose two monads together of any kind. You just need to know this specific thing, and this is not going to be doable for any monad. With option, it is. So with option, essentially what you can do is to take any monad that wraps an option and use an option T to get a flattened representation and to apply essentially the effect of the monad outside and combine it with the behavior of the monad inside. Outside and outside, again, is a little bit imprecise. It works for many examples, not all of them, but for the sake of this talk, I'm going to stick to that idea. So you can use option T directly, and it's the same thing. It's fut opt. It's a little bit different implementation, but it's essentially the same thing to use. Option T, and then you just get a value out. So in general, what you get is that you have two nested things that become a flattened representation by saving somewhere the fact that this piece of data is saved within the data itself, and then you define a flat map over this by using some specific knowledge of bar and the fact that foo is a monad, essentially. You don't need to know anything specific about foo. Let's take another example. It's slightly different, but it looks like it could work. You have three methods, which is get user, get age, and get nickname. The first one returns a future of an option of a user. The second one returns the age of a user in a future. And the third one just gets you a nickname, maybe, if the user has one. And let's use it to compute a late nickname like myself. Gabriele27 is my nickname. So let's go ahead and try to do our computation. So it would be something like this, right? You get the user, you get the age, you get the name, you have some future and options around, so you just wrap everything inside the option T and it works. It doesn't. Why? Well, you need to make the types fit. And this is essentially what it feels to be doing when you're fiddling with this, which is the bad part of working with these kind of things. You need to do this and why. And the first case is fine. Get user is a future of an option of an int of a user, and it's fine. The second and the third, they are slightly different. The first one here is future of an int, so you're missing an option there. And liftf is exactly what it does. It uses the knowledge of how to produce an option from a value, and it uses it and gives you an option T back. Liftf. It's, I think, liftm in Scalar Z, if you care about the differences. And from option T, it does another thing, which is you're missing the future around it. So it takes an option and it gives an option T by using the knowledge of how to produce a future out of an option of something. This is annoying, honestly, and this is why we will see later there is some limitations in using monad transformers. Let's take the last example, which is about updating a user. This is a reasonable use case. You need to check whether a user exists. You need to check whether it can be updated, and then you have to update it on the DB. So you have a future of an option of a user, a future of a Boolean, a future of a user. They're kind of different types. And the problem is if you try to do it naively, you just go and do it, this is some code that you may reasonably come up with. And I try to simplify this further. I failed. Maybe it's not enough coffee. But essentially, you're doing some fiddling with a flat map, then you're matching on the option, then you, well, wait, we're inside of future, so we need to return a future in some cases. useless feature because it's a feature of a none. It just doesn't represent anything. You just put it there because, well, you need to make the type mix together nicely. But then you have to do it again because, well, if you actually a none before, you need to future none here. It's complicated. And what if we want to have more detailed errors, right? Option just represents it's not there. Maybe I want to know why, because I'm curious. So you want to represent this as an either of an error or a user, not just an option of a user. And it gets more complicated because now you need to use your error, but then you have to handle this here, then you need to handle this here. It's getting messy. Future of either of A of B. Does it ring a bell? Probably, because there is an EitherT, which is another transformer, that essentially does the same thing as OptionT, but since either has two parameters, it carries them along. So you have EitherT of F, which is the wrapping monad, A and B. So EitherT represents the transformation of an either when you apply something on it, like a future in this case. So what I propose here to get that example better is essentially this. Define a couple of aliases. They're nice, don't bite, and either we define result T as something that takes an F and an A, and it's essentially either T where I decided already what my error is going to be. Okay? This is maybe my pieces of compilation unit or whatever that I want to use this specific data type on. And then I decide, well, actually also I know the F is going to be a future, and I'm going to call that future result of A. So if you're within a context that it's well known, and you know the methods, you just want to care about the composition of these things, what you may want to do, and this is a suggestion, you may want to have your methods all return the same thing, which is a future of result, which is not so cumbersome at the level of the specific method, which is, for instance, wrapping everything in a future, which is, well, this is silly, but you usually have some actual asynchronous computation here. And then you're simply saying, well, with some syntax from Scala, from cats or ScalaZ, you can just say, okay, the user is the right side and my arrow is the left side, and you do the same thing for others. I think this code is fairly reasonable. It doesn't get much more complicated than this in real words if you keep your functions tiny. And then what you get is that you're able to compose things like this, which very much looks like the original example that we had, but this is actually nicer to read. You care about this thing. This is your business logic. You care about composing all the operations and what comes out of it. If you fiddle with types within here, you're really making the information opaque, because the person that is looking at this code, maybe your coworker, it's gonna be confused. But here it's very clear. I'm doing these things. I don't care about the types here. I care about the semantics, which can be conveyed by the types. But in here, I'm kind of doing some wrapping, so I'm giving some nice names. This is a future result. So what I know is that this thing is going to be asynchronous, and it's going to be returning a user, and it's composing those operations. So I think this is nice, and this is sort of a trick that can be used in some cases. But I have some personal tips and warnings about using monad transformers in general. So stacking more than two monads can get bad really quickly. Well, monad transformers are monads themselves. That's the point of monad transformers. So nothing prevents you from composing them together. So you can have a stack that it's an OptionT, of an EitherT, of a whatever T, and then go on. That works, provided that you have time to wait for it to compile. But it can get messy. This example is taken from repository M from Daniel Spivak, which made an interesting project which is called M, which is also known as Less Confusing Monad Transformers. Is an experiment on taking some ideas from F, which is another library I'm going to talk about in a second, and using the construct of Scala. This is the bad example, and this is why you shouldn't compose too many monad transformers together, because when you're going to use them, then you're going to deal with all the differences, and this is not code that it's readable. This is exactly the contrary of the example that I showed before. Other tip, keep your transformers for yourself. If you're using them within as a local optimization to make the code more readable and more composable, just don't tell me. I really don't want to know, because this is specific from a library. It's not a standard Scala code. I don't want to know, and you don't want me to know, because if you want to change implementation and switch from ScalaZ to cats every Wednesday, I don't want to know. So this is a general comment on public methods, of course. And by the way, if you want to get the future option representation of an OptionT or any transformer, you just call value on it. So this is reasonable to do, and just do it before exposing the method to the user. Third, perf. I'm often in the idea that performance needs to be proven a problem. So if your Scala software talks to a database, for instance, you may be just I/O bound. So this may not be a problem. But if performance is a concern to you, be sure to know that wrapping and unwrapping things is a terrible idea if you care about allocations, right? So what we're doing with monad transformer, we're essentially wrapping things around and then unwrapping them and then wrapping it and then unwrapping them. It's heavy on the allocations. So consider benchmarking your code if this is a concern to you, and consider other alternatives. So some takeaways from this talk. Well, monad transformers, they end with the letter T. So whenever you see some type T, it's probably monad transformer. That's a reasonable convention that it's being seen around in functional programming. F of g of x essentially becomes g of t of f of x, so it's a flattened representation of the same thing, which represents the transformation of one monad, g, with some effects from f, which is the wrapping monad, or the interleaving monad, the one that is right above it in a stack. They can be stacked indefinitely, but don't. And they're one tool for stacking effects. What I've done here is essentially taking a local problem, optimizing it locally, and then having a nicer solution. But you can take a step further back and look at other alternatives. So if you have a complex program that composes monads together in a non-trivial way, and you have maybe more than 2, 3, 4, whatever, you have a reader, you have a writer, you have some complicated stack, you may not want to use monad transformers at all. So a possible approach to do what I've done before, which is separating the business logic from some kind of low-level details, is using free monads. So free monads have the purpose of separating the building of a data structure from the interpretation of the data structure, which is sort of what John talked about before in DSLs. We're lazy, we don't want to do work, so let's separate the two. This does not directly solve the problem of nesting monads, but at least separates clearly the program from the problem of interpreting the program, which is a good help, and it's a very valid approach compared to my tiny trick before of separating the implementation and the composition of the DSL, so to say. In those cases where functions, it's not a DSL, and this is exactly the point. So there's a nice introduction to free monads on the type level documentation, and plenty of others around, including from John. F is another alternative to this problem, and it's precisely targeted at composing effects in a more flexible way. So it's exactly the idea that you can define a stack of effects and then work with just parts of it. And it's really, really nice. I was doing this talk in another conference, and I never used F in real life. And a guy came to me after the conference and showed it to me, and it was amazing. I mean, you can actually do some interesting work with it. So if you have a complicated stack, you just don't want to do a local optimization, I really suggest to delve into this. I was really scared of it, but it's actually pretty nice to work with. This is a project, the specific one I'm linking here is from Eric Torbor, that works for Zalando, that is maintaining the Scala version of F, which comes from the Haskell word, and this is the original paper that introduced it. So this is a very reasonable alternative. You'll find talks online about like the difference between monad transformers and F, and I suggest you to check them out. This is a more systemic solution. It actually tackles the problem at your whole code base level instead of a local optimization like monad transformers can be. So, well, thank you. And I hope you enjoyed the talk. If you have any questions, I'll be here around. And, well, otherwise, I'll just publish the slides on my Twitter, and you can see them there. Thank you.